Hey everybody, Dr. A here, and in this video we're going to be providing some background information on the shear stress-strain diagram. So let's go ahead and dive into it. First thing we want to note is that it is going to be quite similar to the axial or normal stress-strain diagrams that we've studied before. There will be some key differences that we're going to talk about later in this video, but in general it's pretty similar to stress-strain diagrams and relations that we have seen previously. Next, we want to note that a shear stress-strain diagram is commonly developed from either a torsion test or a direct shear test. So you might remember when we were dealing with axial stress-strain diagrams, those were developed, you could develop those from either a tension test or a compression test, although we normally see it developed from a tension test. Here, we develop these from one of two tests, again, either a torsion test or a direct shear test. And so what happens in either of these tests, whether you develop it from a torsion test or a direct shear test, you're going to develop a shear stress in a specimen, and then you're going to have an accompanying shear strain in that specimen, okay? So let's talk about each one of these tests very briefly, okay? Let's start with a torsion test. So if I come over here and I say torsion test, okay? Typically what we do in a torsion test is we have a shaft, which usually will have a circular cross section. And let's give it some kind of length here. Okay, you have this shaft here. And the shaft is subjected to a torque moment. Draw that a little bit better for us. A torque moment T. Okay. Now what happens is the cross section of this shaft is twisted, all right, due to this torque moment T that's applied, okay? So if I were to draw this out as a cross section, let's say that I kind of blow this up and I look at this cross section of the shaft, and, you know, let's say that here's that torque moment T that is causing a twisting action. What happens is you're going to have this shear stress that radiates from the center of the shaft to the edge of the shaft, okay? And it's going to radiate kind of like this, and you're going to have this shear stress distribution, okay? And you're going to have a maximum value, tau max, at the edge of the shaft, and it's going to be 0 at the center of the shaft, and it's going to linearly increase from 0 at the center to a tau max at the edge of the shaft, okay? Now, what happens along the length of the shaft is if I were to sketch a longitudinal line along the length of the shaft, what's going to happen, let me draw that a little bit better for us. Ooh, it's getting worse. Trying to just draw this straight line for us. Let's just do it right here, okay? There we go. That's better. So we got, sorry, that took way longer than it should have. Let's say we have this longitudinal line that's in purple here. What happens is when this shaft is twisted, then this longitudinal line is going to twist and deform, okay? And so what this will end up looking like is something like this. You know, you're going to have this point right here is going to end up moving some distance away, and you're going to get this kind of slice of some sort here along the edge of the shaft, okay? So you see that this has rotated, and what has developed here is this little angle right here. Well, this is a measure of shear strain gamma, okay? That's the change in angle between longitudinal lines along the length of the shaft the original longitudinal line before loading, and then the deformed longitudinal line after loading, okay? Now, we're going to talk more about this phenomenon when we fully explore torsion in some later videos. I just want you to get the idea, the concept of the torsion test, okay? So regardless, with this torsion test, you have a shear stress that develops in the cross-section, and then you have an accompanying shear strain that develops along the length of the shaft itself. What about the direct shear test? Okay, that's another common test that we can use to develop a shear stress strain diagram. So let's call this direct shear test. Okay, in the direct shear test, what we have is a specimen. Usually it's kind of a block shape, and we apply a shear force at one end of that block shape. And let's say that this shape is maybe like fixed at its base, okay? Now what's going to happen is this block is going to deform, all right? So it's going to maybe deform something like this, okay? And this angle of deformation, that's going to be shear strain gamma, okay? Now, the shear stress that develops, which we'll call tau, is going to be equal to that shear force V over the cross-section area of that block. So where is A? Where is the cross-section area here? Well, that's going to be along this surface or in the cross-section of this block right here, okay? So this is a two-dimensional view. If I were to draw this maybe in 3D, you know, I would have something that looks maybe something like this. Here's a 3D view, and, you know, V is right here, and then that cross-section area is this top area right here. So if I want to label that, I could say, you know, this shaded area, that's A, all right? And so from either of these tests, what we can develop is a shear stress strain diagram. So what's that going to look like? Well, let's draw some axes here. Let's say I got some axes. The vertical axis is going to be the shear stress, and the horizontal axis is going to be the shear strain. Now, the shear strain, if you recall, is going to be measured in radians, okay? And so when we plot this shear stress strain diagram, again, we're going to have a shape similar to what we have studied before with axial stress strain diagrams, but with a few differences, okay? First, we are going to have this kind of linear elastic region, all right? And then we're going to transition pretty quickly into this non-linear region, and then we're going to have a failure over here, okay? Now, here are some key things to note here. First, we're going to have a slope of the linear elastic region. This is going to be labeled as G, okay? So G is the slope of the linear elastic region, or the curve. And this is also called the shear modulus, or I'm going to say AKA modulus of rigidity. Okay, so anytime you see G, it's the slope of the linear elastic portion of the shear stress strain diagram, and we call that the shear modulus or the modulus of rigidity. It's got two possible names there. Some other important things to note here, okay? Here at the end of this linear elastic region, you're going to have a proportional limit shear stress and a proportional limit shear strain. So we have tau proportional limit and we have gamma proportional limit, okay? Now, here is one of the key differences, and we're going to list this out here in a minute. The proportional limit values of shear stress and shear strain are very close to the yielding values, okay? So with a shear stress strain diagram, we do not have as well of a defined yielding zone like we did before, okay? So we want to make a note of that, okay? And we'll make a note of that here in just a second. The next thing we want to label here is we have an ultimate shear stress. Okay, this will be tau ultimate. And then, of course, we'll have an accompanying ultimate shear strain. And then this last point over here is the failure or fracture values. So that's tau F, comma, gamma F. Actually, let's label those the other way around. X, comma, Y. That'll be gamma failure, comma, tau failure. Okay? So again, pretty similar, but a couple of differences. Okay? And again, we want to note this proportional limit value is pretty close, almost the same as the yielding values. So we can make a note here. We can say generally tau PL is approximately equal to tau yielding for most materials. Okay, so let's scroll over and let's talk about some of these key differences again. Okay, number one, we just said this. There is not so much of a well-defined yielding zone on the tau gamma diagram. Okay, that's what we were talking about right here. When we looked at the axial stress strain diagrams, there was a more defined yielding zone, but here not so much. Okay, the other key difference is that the shear stress strain diagrams generally do not have necking occur. Now, if we go back and we look at this diagram, this zone right here is similar to the necking zone that we saw with an axial stress strain diagram, okay? But we don't really think of it as necking when we are thinking of shear stress strain, okay? The reason is because necking is really a phenomenon that occurs in tensile loading, and it occurs when you have a localized quick decrease in cross-section area. That's not really what's going to physically happen in a torsion test or in a direct shear test, okay? I mean, it could maybe happen with some materials in a direct shear test, but it's not really physically the same as the necking that we think of in a tension test, okay? So even though you do have this kind of quick decrease in shear stress with a quick increase in shear strain, we're not really going to call this necking, okay? Although mathematically and data-wise, it's similar, but it's not quite the same. So we made this note here, do not really have necking, okay? Let's talk about some last key relations here. Hooke's law is valid in the linear elastic region. That means Hooke's law for shear stress and strain is going to be tau equals G gamma. Where did I get that from? Well, go back here. We said the slope of this linear elastic region is called the shear modulus. That's G. Well, slope is equal to tau PL over gamma PL. So could I write this as the following? I could say G is equal to tau over gamma in the linear elastic portion of the curve, okay? And so all I did was I said, okay, slope is rise over run, and then I rearranged it, and I got tau is G gamma, which is just a form of Hooke's law. That's it, okay? And then finally, we can relate G, E, and nu by the following relationship. So G is shear modulus, E is modulus of elasticity, which we studied before when we were dealing with the tension test, and nu is Poisson's ratio. And so the way they're related is we say shear modulus G is equal to modulus of elasticity E divided by 2 times the quantity 1 plus nu. And what's great about this is we're relating these 3 material properties together. So if you have any 2 of them, you can solve for the third one by just rearranging this equation accordingly, okay? So that concludes this background video on the shear stress strain diagram. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.